Hello. And what we're going to be talking about today is more kinematics, but this time, whereas all the other problems that we've done before, we're pretty much doing kinematics along a horizontal surface. Sometime on that slight angle, we're going to be dealing very much now with motion in a vertical axis. And specifically, stuff like when you drop objects or throw them upwards, what happens, right? And so what we're going to do is we're going to watch some videos, we're going to talk about things and come to some conclusions. So here we go. First off, a quick video to show, and here we go. So I'm getting a different view of my kitchen, and stop. So what I'm doing there is holding a piece of paper and a book about the same height off the ground. Yes, it's not as good as I would like it. The book is slightly higher, but let's pretend that they're being dropped from the same point at the same time. So if I let them go simultaneously, which object is going to hit the ground first? So stop and think for a second. Which object is going to hit the ground first? And then let's see. And there you go. You probably said to yourself, of course the book is going to hit the ground first. Why wouldn't the book hit the ground first? We see that all the time as an observation, right? Our observation of nature seems to be that heavier objects fall faster, right? That's sort of our normal way of seeing things. Specifically here, we saw that the book hit the ground before the paper did. Nothing weird about that set of observations, and they're very much that, exactly that. A set of observations about what we normally see in our daily experience with stuff. But there are some problems with this idea that heavier objects fall faster, that the book hit the ground before the paper hit the ground, okay? And what we want to do is explore those ideas and see what's really going on. So here, I'm just going to start this up again, do the demo again, book, paper from the same height. There you go. So setting up, and this time I think I've got it a lot better. Before we get into that, I think we want to talk about is just a very quick proof of not only does the book fall, what we want to say here is if we're making an observation is that the book specifically accelerates. And what evidence could you offer that the book is accelerating? I'll let you just think about that for a second. You want to stop the video, and there we go. And then you should be back. What evidence could you offer that the book accelerates? Well, very specifically, I wouldn't want to just leave it at accelerates. Specifically, what is the nature of the acceleration? I think we would know it is speeding up, right? But what is our evidence? It'd be very hard to do this because remember, we were talking about what our brain actually does is it's taking visual cues about distance and time. That's very hard to see in this. But a very quick proof of the fact that this book accelerates is initially, what is its velocity? Well, because this is a dropped object, its initial velocity, by definition, has to be 0 meters per second, because that's what it means to drop. If it had a non-zero velocity, it would be a thrown object. So this is just a dropped object. And what we could easily see is that every time after the instant which I let it go, it has a velocity that is non-zero. So the fact that this thing changes velocity, we know that there must be an acceleration acting upon it. Okay. And the reason is because V's magnitude at every other time is greater than 0. Now, I didn't make a declaration here. That's why I didn't want to get into signs here. But I can think we say whether up is positive, down is positive, the magnitude of the velocity is greater than 0 at every moment after t equals 0. And that is sufficient to show there was a change in velocity and therefore that this object was accelerating. And that's really what we want to talk about is what is this acceleration. So now I'm going to do the demonstration again, right? Once again, two objects drop from the same height at the same time. We, of course, are going to expect the book to hit the ground first, right? But then there's a wrinkle. And there you go. If we look back at this, folks, and look at that object, and what I'm going to do, actually, I didn't want to do double speed. I wanted to see if I can do less time. But here you go, drop it. And you can see that at all points here, that those two things are pretty much falling simultaneously, right? What on earth happened there? We had two objects that were dropped from the same point at the same time, and then the book hit the ground. And then notice here, what's wrong with our initial observation? Well, what I hope you see in this second thing with the crumpled up paper and the book, that not only do they hit simultaneously, but also at each moment, they have the same total displacement, right? They were just tracking down at the same time. And so we're going to make some extrapolations about that. So they hit it simultaneously, and at each moment they have the same simultaneous total displacement. Boom, down that they go. And so what changed? Well, if we go back to our original thing, heavier objects fall faster. By crumpling up the paper, do you know what doesn't change about the paper? What doesn't change about the paper is its weight, right? It is still the same heaviness. So apparently, this idea that heavier objects fall faster is not true. Now, it's true sometimes, right? But because it is not a true statement, we can't take that as sort of like an axiomatic basic thing that we want to talk about. So where do we actually get the notion of heavier things fall faster? Well, actually, that was given to us by a gentleman whose name was Aristotle. Aristotle said many things in the 200, 100 BC, that sort of era there, right? Among those, he said that heavier things fall faster. And how did he come to that? Well, Aristotle's big idea when it came to science was the idea that we observe the world as we experience it. Right? He was very much about that our physical experience of the world reveal the truth about the world. And these observations, as he would say, would reveal the truth about the world. Right? Essentially that we could trust our senses, that our senses were the guiding light in terms of what was going on. But apparently that leads to all sorts of really false conclusions. And for reasons we'll talk about in a couple of minutes. So what is it that changed when I crumpled the piece of paper up that caused the simulation to go differently? Well, certainly it wasn't the weight of the object that changed. And what we realize is, and I'll let you think about that for a second, what do you think changed? And hopefully what you realized is that what came into play in the first situation that didn't come into play in the second situation was air resistance, right? And you've had that experience before. You stick your hand out the window of a car when it's not moving, no big deal. But when the car is moving, you feel that resistance against your hand. That's air resistance. And so if I'm sticking my hand out the car, if I don't want to feel that as much, what do? I turn it on its side, right? That surface area, frontal surface area, affects the amount of air resistance that I experience. So what ended up happening here is by reducing the frontal surface area of the paper, what I ended up doing was I made air resistance negligible. Okay, or a better word that you're more familiar with is insignificant, where it was very significant when the paper is flat. And then for the book, for reasons we'll talk about, that amount of air resistance that it was experiencing was insignificant for it over that distance. So the book, even though it was experiencing air resistance, was never really affected by it that much. By reducing the frontal surface area of the piece of paper, we made the air resistance also negligible for it. And what we ended up doing was we removed a confounding variable from the experience, such that now the only relevant thing that was acting on both the piece of paper as well as the book was the force of gravity. Whereas before, on the piece of paper, gravity was significant, as was air resistance. And it wasn't until the 1500s that we get someone who kind of figures all of this out. Who is that person? Does anyone know? I'm asking a blank computer screen, but think to yourself, who 1500 scientists? And hopefully you've said to yourself, Galileo. Galileo was really important in the development of our modern notions of science because, unlike Aristotle, who said, observe the world as it is, Galileo understood that if you didn't look at one action and the consequence of one action, that you could never really figure out anything because you would never know what the combinations of variables was. And so what we owe to Galileo in a book that's called The Two New Sciences, by the way, we'll come back to the Two New Sciences later on in the course of the year, is he says, just from a philosophical sense, is that we have to examine the ideal situation. And the ideal situation is one in which there is a singular cause leading to a singular outcome. And that should sound really familiar to you from your modern studies of science, right? That's that notion of that we only test one variable at a time, and a good experiment holds everything else constant and just manipulates one variable to look at the outcome. That notion is a fairly new notion, right? New in terms of scientific history, and it comes from Galileo largely, or at least adopting it into our modern parlance is from Galileo. Certainly, there were other cultures that came to that understanding. I wrote about it long before Galileo ever did, but just in a Western sense, just to be perfectly frank, Galileo is what impacted our sense of modern science. And so we owe to Galileo that notion of good scientific method, one variable tested to see the outcomes. When Galileo looks at this, he says, okay, well, what I'm going to tell you is if we're going to do this, we're going to come up with something that he then calls, or we now call Galileo's law of falling bodies. And so what did Galileo do? Well, he said he recognized that air resistance was a confounding factor. He said, if only the force of gravity acts, then two objects, even of disparate mass, meaning different masses, when dropped simultaneously from the same height, will land at the same time. Okay. You might have heard an old wives' tale that Galileo went up to the top of the Leaning Tower of Pisa and dropped things. Nope, didn't happen. That's just a cute little myth. What Galileo did do is off a second-story window, dropped a small cannonball and a large cannonball in order to observe this. Not good for the underlying ground, but there you have it. And so Galileo makes this statement. Now, this statement has a lot of corollaries to it and a lot of caveats to it. So if only the force of gravity acts, that is the confounding position here, right? Notice I'm using the word law. A law is always true within its given context. So there's the given context. If the only force that's acting is gravity, the second you have any other force, this is not going to happen, right? And it doesn't make the claim that this is going to happen either. So next about that, this is a very specific type of law, because notice, what does this law not explain? This law does not explain why the statement is true. It only says, if this condition, then this always happens. This is what's known as an empirical law. So an empirical law is a statement of what will happen, not why it will happen. Okay? So empirical law rather than a theoretical law or an analytical law, which are going to explain the why of things, not just the what of things. It's a very important empirical law in the study of science. So let's look at the corollaries of this. So the first corollary of this is if they hit the ground at the same time, that means that if we have two objects that have the same VI, right? VI is the same, 0, dropped, okay? That they go equal distances. So let's say the displacement, actually we'll go y displacement of object 1 is equal to the y displacement of object 2, and their times are the same, that something else is the same. Well, if I look at our equation of motion, VIT plus 1/2 AT squared, and actually I'm going to put a y subscript on both of these things because that's meaningful since I'm being more specific to the y dimension right now. You'll notice then, if this is the same, and this is the same, and this is the same, and this is the same, that must mean that the first corollary of Galileo's law of falling bodies is that all objects moving with only gravity acting have the same acceleration. Okay, we're going to give a name to that in just a second, and then I want to talk about the second corollary. So going on to the next equation, VF is, let's say VFY is VIY plus AYT. So now if they have the same initial velocity and the same time and same acceleration, that must mean that these two objects, whoops, move that up, are going the same velocity at any moment, right? Those two simultaneously dropped objects. All right, now this is the thing that we most care about. This idea that all objects moving with only gravity acting on them have the same acceleration. We're going to give a name to that. That is going to be called the acceleration due to gravity. And there's another name for it. It is often called the free fall acceleration. You may have heard that term before, free fall acceleration. Free fall is any situation where only gravity acts. Now, in our world, oftentimes air resistance is impossible to ignore. So we're going to have a slightly lower standard for this, not a situation where only gravity acts, but where gravity is the only significant force acting. Okay. Otherwise, we get too into the weeds too quickly, and it's actually not all that interesting. So for our purposes, we're going to largely ignore the impact of air resistance because it's going to be insignificant for most of the things we're doing. We'll talk later for those limited number of times where it's significant, but I'm going to tell you the math gets way more complicated. So what is this free fall acceleration? Well, acceleration to gravity, free fall acceleration, this comes up so often, it's actually given its own symbol, right? It's little g. Now notice I say little g, not big G, because big G is going to be something different, right? So little g, the acceleration due to gravity. Please don't call it gravity, because it is not itself gravity. Gravity is a concept. Little g is a number or a quantity, right? It is not the embodiment of everything gravity. So let's be precise in our statements. It is the acceleration due to gravity, little g. It's going to have another name as well. I'm just going to throw this out here for the moment, and we're going to circle back to it in around about December, January. It's also called the gravitational field strength. Actually, we'll cycle back to this in a couple of weeks, right? And so it has a lot of identities. It's a bit of a chameleon, but there it goes. Now, what makes this helpful is that it's actually a very well-known quantity. Actually, I don't want to look at myself here. A very well-known quantity. I will say, on Earth, on average, at sea level, the value of the acceleration due to gravity is 9.8 9.81 meters per second per second. Now, in this class, we're just going to use 9.8 meters per second. Yes, it's less precise, but just roll with it. And some limited times, we might even want to go one less precise and just say it's about 10. But I think that's a little bit overly simplistic. So we're going to be using in this class 9.8 meters per second per second. So therefore, G equals 9.8 meters per second on Earth, on average, at sea level. We'll dig into that in just a second. The next thing I want to say is that this is a certain quantity. But in a problem, what I would say is something like this. The vertical acceleration is, and then I would need a declaration. Let's say I say down is positive. Then the vertical acceleration would be positive g. Okay? G is this number with these units. And then if I want to talk about it as an acceleration, I would have to assign it directionality. If I say up is positive, then AY for an object in free fall would be negative g. And then depending on the context of the problem, you might make different decisions there. But g is the quantity. And then when I want to turn it into a vector, like an acceleration, then I'm going to call it positive or negative based on what my declaration is in the vertical direction. So now, that's great, because that means if I throw something upwards or drop something downwards, I know it's acceleration. So you're going to get all these problems where it'll look like you don't have enough information, and then you'll say, oh, the object's in free fall, I know the acceleration of that object. So let's just deal with on Earth on average at sea level. At different locations in space, and I literally mean in space, because on Earth, the acceleration due to gravity is different. Notice here we called it the gravitational field strength. For reasons we'll talk about later, different planetary-sized objects have different gravitational field strengths, and little g is a statement of that. Just to give you a little flavor, G on the surface of the moon is about 1.67 meters per second. G on the surface of Mars is about the same as on Earth, but it's actually 0.05 meters per second. Jupiter on the surface of Jupiter would be about 30 meters per second. Now that's problematic because you can't be on the surface of Jupiter because, that's right, Jupiter is made of gas. There is no surface to stand on, but if we were to measure this quantity at that location, we would find that. And actually, Galileo does a lot of work in the book, Two New Sciences, for deriving the value of this work, and then we've done more and more work over the years to get more precise values. But interestingly enough, that's on Earth, on average at sea level. What we've also found is as altitude rises, so as you go further away from the sea level, little g decreases. Now, here's the thing. It doesn't decrease by all that much. Little g on the top of Mount Everest is about 9.78 meters per second. It's really not all that much bigger. So altitude doesn't have this massive impact because actually Mount Everest on a universal scale, that height away from the Earth's surface is really not all that far. People who talk about, at the International Space Station where they're going around, the value of little g is actually significantly decreased but it's not zero, right? Those people say, oh, gravity doesn't affect them. That's wrong, but we'll get back to that later. And then last, on average. Here's just a weird fact. that there are different places around the Earth where locally G is much higher or lower. For example, in northwestern Pennsylvania, the local value of G is a little bit higher. It's like 9.82 or so. And in Costa Rica, the local value of G is a little bit lower, around about 9.79. And what causes these weird fluctuations? Well, the Earth's crust is not of uniform density. Northwestern, Pennsylvania, a lot of coal mines, a lot of iron mines. And that local density of the Earth's crust causes little g's value to be up. Costa Rica, made largely of limestone. If you've ever been there, the beautiful caves and all that stuff near the shore, the local density of the Earth's crust is less there. It causes these fluctuations. In fact, NASA has a satellite that is constantly going around the Earth that measures that fluctuation values in little g. And actually, that's how we have evidence that fracking actually causes significant implications on the local structure of the Earth's crust that go far beyond just the local area where the fracking is being done, because we can see changes in the value of little g at various areas. And we've been tracking those changes for quite some time, showing that there is actually definitive proof that there are permanent changes happening to our ecosystem through that. Now, what the meaning of those are, I'm not going to debate that with you, but the reality of them, I'll debate that from beginning to end if you think that fracking doesn't have an implication. But let's just put that aside and talk. So on Earth, on average, at sea level, our problems, unless otherwise stated, are going to be on Earth, on average, at sea level. So you can take a dropped object or a thrown object and always know that that acceleration due to gravity is 9.8 meters per second downwards, right? Always downwards. Constant in value and downwards. Always, always, always. Hold on to that. That's going to become really important next week. So there's another video that is also posted with this assignment, and that video is going to show you a really neat thing, which is what happens if you drop a feather in a bowling ball in a vacuum, meaning that you didn't have air resistance. It's a little over dramatic, but it is a neat little thing. So enjoy the watch on that as well.